Hello, everyone present. Our work's title is CNN Approach Implemented to Emotional Facial Expression Recognition for the Prevention of Autistic Meltdowns. I am Ítalo Oliveira. We are from the University of Acre, Brazil. This study presents an approach based on computer vision techniques for real-time monitoring of individuals' emotional facial expressions. Individuals affected by autism spectrum disorders show impairments in several areas of development, including reciprocal social interaction, communication, and emotional processing. The approach is implemented in a model called MOTA to be used to monitor individuals with autism spectrum disorder who may have a meltdown. Let's talk about the implementation details, starting with the dataset. The dataset used in this work was FAIR+. FAIR+ is considered an improved version of the FAIR 2013 dataset. It was published in 2016 by Microsoft in a paper that talked about the performance of FAIR 2013. So they decided to relabel the FAIR 2013 image, creating FAIR+. It has the same structure as FAIR 2013 with the same image, but with the added emotion of content. In the image, we can see a small comparison of the FAIR 2013 dataset with the FAIR+, where the upper labels are from FAIR 2013 and the lower labels from FAIR+. To start our proposal, we have the following flow with the steps of the proposed system. An image is captured by a camera or webcam. Then this image is passed through the face detection model. The face is cut out of the image and sent to the facial recognition model. And finally, the main objective, which is the recognition of facial expressions. The image is resized to 14:8 by 14:8 size. Pre-processing is applied, then the proposed CNN will perform the emotion rating. In order to facilitate implementation and improve performance in MOTA, BlazeFace was used. BlazeFace is a facial detector for real-time inference. For facial recognition, a pre-trained CNN was used, the Inception ResNet. However, this feature has not been implemented in the current version of MOTA. In the image below, it's possible to view the detection and facial recognition in operation. The proposed CNN is a VGG-based architecture, so you can see some convolutional layers stacked with a pooling layer right after. The activation functions used in the convolutional layers and fully connected layers was the ReLU function. A dropout rate of 20% was used. At the exit, the softmax activation function was used. And for training the network, batch of 256 samples and the ADAM optimized were used. The tools used to implement CNN were Python language with machine learning libraries, TensorFlow, and Keras. Google Colab was also used so that it was possible to train the network using the GPU. The FAIR Plus dataset was divided into 18% for training, 10% for validation, and 10% for testing. For network training, we use data augmentation. This technique adds small transformations to training images without increase the number of samples. In this way, it is as if we are training the network with more images than we have, increasing the generalization of the network. About the results obtained with the proposed CNN, the efficiency of the proposed CNN was evaluated using accuracy and loss graphs in the training and validation process. The percentage of accuracy in the test reached the maximum value of 18.6% in 60 times. In the confusion matrix, the test step presented the following results. On the y-axis, we have the correct classification, and on the x-axis, the predicted classification. It's noted that there was a much higher rate of correct answers in the emotion neutral and happy emotion, and a superficial rate of correct answers in the emotion disgust. But these results did not bring problems to the test performance. The class of emotion that are related to a meltdown, anger, and sadness had good results. The contempt emotion did not get in right because of the used architecture. Because it is a simple architecture, it has not been able to generalize to this emotion class. About the emote model, following the flow of the diagram, we start with facial detection, followed by facial expression recognition. From the recognition of emotions, we have a decision making. If the detected facial expression is a trigger for meltdown, then the system must alert the professional and show the palliative measures. Otherwise, he continues monitoring. Another essential feature of the system is the ability to accept all the trained CNN modules, allowing you to easily and quickly change the CNN model that will recognize expressions. In the image, we have the screen where it's possible to insert a JSON file that describes the network architecture and a set of binary files that contain the trained waves of the network. These screens display essential information about the individual, such as anamnesis and palliative measures. About the experimental results, as one of the main results of the implementation of the multi model, it's possible to observe the individual monitoring contain the detected face with the identified expressions. It's also possible to identify 12 the colored bars, the percentage of each expression detected. In the figures, the results of the multi-model are shown with expressions recognized in tests with different lighting levels. We test with 3 types of lighting: artificial light, natural light, and low light. In this image, we have a high percentage of recognition for the sadness emotion. In general, emotions that can be considered trigger points, such as anger and sadness, had favorable results. The fear emotion is very confused with the surprise emotion due to the open mouth and wide ears. Completing the work, in this paper is present an approach using deep learning algorithms to monitor individuals in real time using the recognition of their emotional facial expressions, allowing the preventive identification of a meltdown. The proposed approach is based on a properly customized CNN. Using the FAIR+ database, experiments carried out show that it is able to obtain a good classification accuracy for the application purpose, equivalent to 18.6%. Considering that the model was tested in unfamiliar environments and with variable lighting conditions, the detection and recognition results also show behavior with good performance. Tasks performed on the model, such as facial detection, presentation of anamnesis, and palliative measures, reinforce the conclusion that the prediction of emotional facial expressions becomes a successful possibility of social relevance. The model can be used both in the health area and in education, aiming at monitoring patients and students. Thank you all.